In 1956, a Navy physicist named Lloyd Berkner stood in front of a room full of admirals at the Office of Naval Research and proposed something that made half of them walk out. He wanted to abandon sonar, the technology that had won the Battle of the Atlantic, and instead hunt Soviet submarines by measuring invisible traces of radiation in seawater. The admirals called it science fiction. Berkner called it physics. The problem was urgent. The Soviet Union had just launched its first nuclear-powered submarine, and American sonar operators were discovering that tracking a vessel that could stay submerged for months was fundamentally different from hunting diesel boats that had to surface regularly. Traditional active sonar gave away your position. Passive sonar required the target to make noise. Soviet engineers were making their submarines quieter every year. By 1957, the Navy's detection ranges had shrunk to less than 5 miles in good conditions. In the Norwegian seas, thermal layers, sometimes less than 1. Berkner had spent the war years working on the Manhattan Project at Los Alamos, measuring radiation signatures from plutonium production reactors. He understood that nuclear reactors don't just generate heat, they create dozens of unique radioactive isotopes. When seawater passes through a submarine's reactor cooling system, it picks up trace amounts of these isotopes before being discharged back into the ocean. Theoretically, you could detect a submarine not by listening for it, but by analyzing the water it left behind. The theory was sound. The execution seemed impossible. The concentrations Berkner was talking about detecting were measured in femtocuries per liter, quadrillionths of a unit. Seawater already contained natural radioactivity from cosmic rays and uranium deposits. The signal-to-noise ratio looked hopeless. Even if you could build a sensor sensitive enough, how would you process samples from entire ocean basins? How would you distinguish Soviet reactor signatures from American ones, or from nuclear weapons testing fallout that was contaminating every ocean on Earth? The Office of Naval Research gave him 45 days and a budget of $12,000 to prove the concept wasn't insane. Berkner assembled a team of 3 graduate students and a borrowed spectroscopy rig that had been decommissioned from Oak Ridge National Laboratory. They set up in a basement room at the Naval Research Laboratory in Washington, using glass carboys and a saltwater mixture that approximated seawater chemistry. The goal was simple: create a known concentration of reactor signature isotopes, then see if they could detect it against background radiation. The first month was failure after failure. Their detector kept picking up contamination from the building's concrete walls, which contained trace uranium. They tried lead shielding, but the lead itself was radioactive. They switched to older leads salvaged from a sunken 19th century ship, which had been cast before atmospheric nuclear testing began. That helped, but their detection threshold was still 2 orders of magnitude too high. They needed to measure concentrations 100 times smaller than their equipment could reliably register. Berkner started working 16-hour days, sleeping on a cot next to the spectroscopy rig. His marriage was deteriorating. His colleagues at Los Alamos thought he'd lost his mind chasing submarine detection when the real threat was Soviet ICBMs. The Navy's deadline was approaching, and he had nothing to show but pages of inconclusive data and a laboratory that smelled like brine and electronics. Then, on day 42, one of his graduate students suggested something that shouldn't have worked: pre-concentrating the samples through chemical extraction before measurement. The chemical extraction process was elegant in concept, brutal in execution. Berkner's team discovered that certain isotopes produced by naval reactors, particularly cesium-137 and strontium-90, could be separated from seawater using ion exchange resins, the same materials used in water softeners. By running hundreds of liters of sample water through columns packed with specialized resins, they could concentrate the target isotopes by factors of 10,000 or more. What had been an invisible signal became measurable. The physics made sense once you understood reactor operations. A pressurized water reactor, like those in Soviet November-class submarines, ran at temperatures exceeding 300 degrees Celsius and pressures above 2,000 pounds per square inch. The primary coolant loop stayed sealed, but the secondary cooling system drew in seawater, circulated it through heat exchangers positioned near the reactor vessel, then discharged it back to the ocean. Neutron activation, the process where stable atoms absorb neutrons and become radioactive, occurred in trace amounts in that secondary loop. The discharged water carried a unique fingerprint. Elevated levels of sodium-24, cobalt-60, manganese-54, and other activation products with half-lives ranging from hours to years. Berkner's breakthrough was recognizing that you didn't need to detect all of these isotopes. You needed to find the ones with the right combination of half-life and concentration. Sodium-24 decayed too quickly, half-life of 15 hours, making it useful only for very recent detections. Cobalt-60 lasted 5 years but appeared in such low concentrations that isolation required processing thousands of liters. The sweet spot was cesium-137, half-life of 30 years, relatively high concentration in reactor effluent, and chemically distinct enough from seawater that extraction was straightforward. By March 1957, Berkner's lab could reliably detect cesium-137 at concentrations of 1 picocurie per liter, 1/1,000,000th of a curie. They tested the system on samples taken from Chesapeake Bay, where the Navy occasionally operated its own nuclear submarines. The detector lit up. They could see the radioactive wake of USS Nautilus from samples collected 6 hours after the submarine had passed through. The detection range was limited only by how much the isotopes dispersed through ocean currents. The technical challenges of scaling this up were staggering. Laboratory spectroscopy was one thing. Building field-deployable sensors that could operate on the ocean floor for months was another. The detection equipment required liquid nitrogen cooling to reduce thermal noise in the scintillation crystals. The ion exchange columns needed periodic regeneration with acid solutions. The whole system had to withstand pressure, corrosion, and biological fouling, while maintaining sensitivity levels where a single microcurie of contamination would render the sensor useless. Berkner designed a modular system, underwater collection stations that pumped seawater through resin columns continuously, concentrating samples over days or weeks, paired with retrieval vessels that would periodically collect the columns and transport them to shore facilities for analysis. The collection stations could be anchored on the seafloor in strategic choke points, areas where Soviet submarines had to pass on their way to and from patrol areas. The Greenland-Iceland-UK Gap, the Straits of Gibraltar, the entrance to the Sea of Okhotsk. The Navy's skepticism began to crack when Berkner demonstrated that his system could distinguish between American and Soviet reactor signatures. Different reactor designs produced different isotope ratios. Soviet submarines used a different fuel enrichment level and operated at different temperatures than American boats. The fingerprints were distinct enough that analysts could identify not just that a submarine had passed, but which class of submarine it was. The Navy authorized a classified program in June 1957 with a budget that made Berkner's initial $12,000 look like lunch money, but there was a catch. They wanted operational sensors deployed within 18 months. Berkner had proven the physics worked in controlled conditions. Now he needed to engineer a system that could survive the North Atlantic. He set up shop in Building 212 at the Naval Research Laboratory, a concrete structure that had been used for radar development during World War II. The space was 30 feet by 40 feet with exposed pipes, terrible ventilation, and a loading dock that opened directly onto the Potomac River. Berkner requisitioned equipment from every available source: surplus scintillation detectors from Los Alamos, high-capacity water pumps from a decommissioned desalination plant, industrial ion exchange resins from a chemical company in New Jersey, and pressure housings that had been built for deep-sea oil exploration but never deployed. The first prototype collection station looked like something assembled from a junkyard. a cylindrical pressure vessel 8 feet tall and 4 feet in diameter, welded from quarter-inch steel plate. Inside, 4 parallel columns packed with cation exchange resin, each column 3 inches in diameter and 6 feet long. A centrifugal pump capable of moving 200 liters per hour. Valves, gauges, electrical penetrators, and a battery bank that was supposed to power the system for 90 days. The entire assembly weighed 1,100 pounds dry. They tested it in the Potomac in August 1957. The pump seized after 6 hours. Salt water had corroded the motor bearings despite the supposedly waterproof housing. Berkner's team pulled it back, replaced the bearings with graphite-impregnated bronze alloys, added zinc sacrificial anodes, and tried again. This time the pump ran for 3 days before the resin columns clogged with sediment and organic matter. They added pre-filters. The filters clogged in 2 days. Berkner spent weeks solving problems that seemed trivial until they stopped your entire system. Barnacles growing on intake ports, crabs crawling into pump housings, temperature fluctuations that caused expansion joints to leak, battery chemistry that degraded in cold water, electrical systems that shorted when moisture penetrated supposedly sealed connectors. Every failure required disassembly, diagnosis, redesign, and another test cycle. By December, they'd gone through 7 complete prototype iterations. The analytical side had its own nightmare logistics. The resin columns, once saturated with sample, had to be transported to a laboratory equipped with gamma spectroscopy equipment sensitive enough to measure picocurie levels. That meant shielded containers for transport, clean rooms for processing, and technicians trained to handle low-level radioactive materials without contaminating the samples. Berkner commandeered a former medical laboratory at Bethesda Naval Hospital and installed lead-lined rooms with HEPA filtration. The spectroscopy equipment alone cost more than the entire initial research budget. The break came in January 1958 when a marine engineer named Robert Taggett joined the project. Taggett had designed deep submergence equipment for oceanographic research and understood how to build things that lasted underwater. He redesigned the pressure vessel using titanium instead of steel, rebuilt the pump assembly with ceramic seals, and added a back-flushing system that automatically cleaned the filters every 12 hours. The 8th prototype went into the Potomac in February and ran continuously for 47 days before they pulled it up for analysis. The resin columns showed clear cesium-137 signatures, matching USS Seawolf's transit through the area 3 weeks earlier. The concentrations were exactly what Berkner's models predicted. They had a working sensor. Now they needed to build 50 of them and deploy them across 3 oceans without the Soviets noticing. The first operational deployment happened in April 1958, 40 miles southwest of Reykjavik in water 1,600 feet deep. The location wasn't random. Soviet submarines leaving their northern fleet bases at Murmansk had to pass through the gap between Greenland and Iceland to reach the Atlantic. The Navy modified a submarine rescue vessel, USS Petrel, to look like it was conducting routine oceanographic research while actually lowering Berkner's collection stations onto the seafloor. They deployed 3 sensors in a triangular pattern covering a 12-mile corridor. Each station cost $87,000 and represented 6 months of engineering refinement. If they failed, the program was probably finished. If the Soviets discovered them, the intelligence value dropped to 0. Berkner watched from Petrel's deck as the 3rd sensor disappeared beneath gray North Atlantic swells, then spent the next 60 days analyzing seawater samples from a laboratory in Maryland, waiting for retrieval. The plan called for a 90-day collection cycle before the first recovery. On day 62, the gamma spectroscopy results started showing something nobody expected. Cesium-137 concentrations spiking to levels 3 times higher than anything they'd measured from American submarines. The isotope ratios matched Soviet reactor designs. The detections were appearing simultaneously at all three stations, suggesting a submarine moving through the corridor at approximately 12 knots. Then the signals faded as the submarine continued southwest into the Atlantic. Berkner immediately called the Office of Naval Intelligence. They checked their records. No American submarines in that area, no known Soviet surface vessels. The detection was tracking a submerged contact that traditional sonar hadn't seen. The Navy scrambled P-2V Neptune patrol aircraft to the area, but by then the submarine was 200 miles away, and the ocean is a large place to search visually. Still, the point was proven. The sensors worked against real targets in operational conditions. When they recovered the stations in July, the resin columns told a more complete story. 4 separate Soviet submarines had passed through the gap during the 90-day period. The isotope signatures suggested 3 were November-class attack submarines, and 1 was a different design. Possibly the experimental Hotel-class ballistic missile boat that intelligence reports had mentioned but never confirmed. The concentration data let analysts calculate approximate speeds and even estimate when the submarines had last been in port based on the decay of short-lived isotopes. The Navy's response was immediate: expand the network. By December 1958, stations were operating in the Greenland-Iceland-UK gap, off the Kola Peninsula, near the Bering Strait, and in the Sea of Japan. Each location provided coverage of strategic choke points where Soviet submarines had limited route options. The detection rate was remarkable. They were identifying submarine transits that sonar arrays completely missed. But the system had a fundamental limitation that drove traditional submariners crazy. It couldn't provide real-time tracking. The sensors collected data over weeks, which was then analyzed days or weeks after recovery. You learned that a submarine had been there, not where it was now. The intelligence value was strategic rather than tactical, understanding Soviet patrol patterns, identifying new submarine classes, estimating fleet size, but it couldn't vector a destroyer to an immediate target. Berkner argued this was exactly the point. The Navy didn't need another tactical system. It needed strategic intelligence about Soviet submarine operations. Where were they going? How often? How many? What were their patrol patterns? His sensors answered questions that sonar never could because they worked across ocean basins rather than at ranges measured in miles. The admirals who'd walked out of his first presentation were now requesting coverage areas. Scaling from a dozen prototype sensors to a global network required solving problems that had nothing to do with physics. Berkner needed manufacturing capacity, deployment vessels, recovery logistics, shore-based processing facilities, and a workforce cleared to handle classified radioactive materials. The Navy created a cover program called the Sound Surveillance System, SOSUS, which publicly focused on acoustic arrays while quietly funding Berkner's radiation detection network under the designation Project Sand Dollar. The manufacturing contract went to General Electric's Heavy Military Electronics Department in Syracuse, New York. Engineers there redesigned Berkner's hand-built prototypes for production, switching to standardized components and modular assemblies that could be serviced in the field. They increased the pressure rating to 3,000 feet, added redundant pump systems, and integrated automatic data logging that recorded flow rates and operational status. By mid-1959, GE was producing 4 complete sensor stations per month at a unit cost of $62,000. The deployment challenge was more complex. Dropping sensors randomly across the ocean was pointless. You needed to place them where Soviet submarines actually traveled. Naval intelligence provided targeting. The Guyuk Gap remained the highest priority, but analysts also wanted coverage at the Strait of Gibraltar, the Turkish Straits, the waters off Vladivostok, and the approaches to Soviet submarine bases in the Arctic. Each location required bathymetric surveys, current analysis, and careful positioning to ensure sensors sat in water flow patterns that would actually sample passing submarines. The Navy commissioned 6 modified auxiliary vessels designated as oceanographic research ships. They looked identical to legitimate civilian research vessels operated by institutions like Woods Hole and Scripps. Same equipment profiles, same deck layouts, same academic paint schemes. The crews wore civilian clothes when in foreign ports. The mission: deploy and recover sand dollar stations, while maintaining the appearance of conducting marine biology surveys or seafloor mapping. It worked better than expected. Soviet intelligence photographed the vessels multiple times, but apparently classified them as low-priority scientific targets. Recovery operations happened every 60 to 90 days. Vessels would transit to coordinates provided by naval intelligence, lower acoustic transponders to locate the bottom-mounted sensors, then use specialized winches to bring them up. The saturated resin columns were removed, sealed in lead-lined containers, and replaced with fresh columns. The entire process took about 4 hours per station. The recovered columns went to one of 3 shore facilities: the original laboratory at Bethesda, a new facility at Pearl Harbor, and a third at Holy Loch in Scotland. Processing capacity became the bottleneck. Each resin column required 6 to 8 hours of spectroscopy analysis. With stations being recovered every few days, the backlog grew to 4 weeks by late 1959. Berkner brought in additional gamma spectroscopy equipment and trained Navy technicians in analytical procedures that had previously required PhD-level expertise. He developed standardized protocols, baseline measurements, multi-isotope analysis, ratio calculations, and signature matching against a growing database of known reactor types. Analysis time dropped to 3 hours per column while maintaining accuracy. By January 1960, the network included 47 active stations across the Atlantic, Pacific, and Arctic Oceans. Monthly intelligence summaries documented an average of 32 Soviet submarine detections, including boats that acoustic systems never tracked. The data revealed patterns. Northern Fleet submarines operated on 90-day patrol cycles. Pacific Fleet boats stayed closer to home waters, and the Soviets were building submarines faster than NATO intelligence had estimated. Instead of 14 operational nuclear submarines, the actual count was closer to 23. The cost was substantial: $3 million annually for operations, plus $2 million for processing. But the intelligence value exceeded acoustic surveillance systems costing 10 times more. On October 22, 1962, President Kennedy announced the naval blockade of Cuba. What the public didn't know was that Soviet submarines were already in Caribbean waters, and finding them was the difference between enforcing a quarantine and starting a nuclear war. Berkner got a call at 3 a.m. from the Office of Naval Intelligence. They needed immediate analysis on any sand dollar detections in the Atlantic approaches to Cuba from the previous 30 days. The problem was timing. The most recent recovery from stations positioned off the Bahamas had happened 6 days earlier. The resin columns were still in transit to Bethesda. Berkner ordered the courier aircraft diverted directly to the laboratory and had his team standing by when it arrived at 9 a.m. They ran continuous spectroscopy for 18 hours straight, processing 4 columns simultaneously instead of the standard sequential analysis. The results were worse than intelligence had feared. 5 separate Soviet submarines had transited south through the Florida Straits between October 1st and October 18th. The isotope signatures indicated Foxtrot-class diesel-electric boats, which made sense. They had longer range than November-class nuclear boats and were quieter. But the concentration data suggested something unexpected. The submarines were running submerged far more than normal diesel boat operations allowed. Intelligence analysts concluded they must be carrying additional battery capacity or using snorkel operations more extensively than doctrine suggested. The Navy's blockade plan assumed Soviet submarines might try to penetrate the quarantine line, but confirmation that boats were already south of Cuba changed the tactical situation. Kennedy needed to know if those submarines were still in the area or had withdrawn. Berkner proposed emergency deployments, dropping temporary collection stations from destroyers already on patrol, then recovering them after 48 hours. It wasn't enough time for ideal sample concentration, but it might show recent activity. The Navy authorized the emergency protocol on October 24th. Destroyers deployed 23 quick-reaction sensors at pre-calculated positions around Cuba. The sensors used the same technology as the permanent stations, but were designed for rapid deployment and recovery, lighter construction, smaller resin columns, battery power instead of the standard fuel cells. They went into the water within hours. Recovery began on October 26th. The first results showed fresh cesium-137 signatures within the past week at stations north of Cuba. The concentrations were lower than ideal, but the isotope ratios were unmistakable. Soviet submarines were still operating in the blockade zone. More critically, the detection patterns suggested they were patrolling in a specific area northeast of Havana, possibly positioning to attack the blockade force if orders came. Berkner's data went directly to the Joint Chiefs. They vectored P-2V patrol aircraft and sonobuoy patterns to the indicated area. On October 27th, aircraft located and tracked a submerged contact matching the predicted position. Destroyers moved in with active sonar and depth charges, practice charges not armed, but the message was clear: we know you're there. The Soviet submarine surfaced. Later declassified Soviet records confirmed it was B-59, one of 4 Foxtrot-class boats that had been ordered to protect Soviet shipping to Cuba. The radiation detection network didn't prevent the Cuban Missile Crisis, but it provided intelligence that shaped how the Navy prosecuted the blockade. Kennedy knew Soviet submarines were present before surface contacts occurred. The Navy knew approximately where to search. The tactical advantage was marginal, hours rather than days. But in a crisis where miscalculation could trigger nuclear war, hours mattered. When the crisis ended, Berkner received a personal letter from the Chief of Naval Operations. It didn't mention Sand Dollar by name. The program was still classified. But the meaning was clear. His sensors had proven their value under the worst possible conditions. Soviet naval engineers weren't stupid. By 1963, intelligence reports indicated they were analyzing water discharged from their own submarines and discovering what Berkner had known for years. Reactors leave radioactive fingerprints. The technical arms race began immediately. Soviet designers started developing closed-loop cooling systems that would reduce or eliminate radioactive isotope discharge into seawater. The first countermeasure appeared in late 1963 on newer Victor-class attack submarines. Instead of discharging secondary coolant directly overboard, the system routed it through ion exchange beds similar to what Berkner used for detection. The Soviet version stripped cesium-137 and other isotopes from the coolant before discharge, theoretically making the submarines invisible to radiation detection. The Navy retrieved Sand Dollar stations from the Barents Sea in January 1964 and found dramatically reduced signature levels. The system that had worked flawlessly for 5 years was suddenly detecting only a fraction of known submarine activity. Berkner's response was to go after different isotopes. While cesium-137 was easiest to detect, submarine reactors produced dozens of other radioactive species. He focused on activation products created in the reactor's structural materials: cobalt-60 from steel components, manganese-54 from stainless steel, and tritium from the water itself. These isotopes formed inside the reactor vessel and appeared in coolant through corrosion and neutron activation of dissolved materials. Soviet ion exchange beds were optimized for cesium and strontium removal, but were less effective against these alternatives. The technical challenge was sensitivity. Cobalt-60 concentrations were roughly 1/10 of cesium-137 levels, requiring either longer collection periods or more sensitive detection equipment. Berkner's team at General Electric developed improved scintillation crystals using sodium iodide doped with higher thallium concentrations. The new detectors could measure cobalt-60 at concentrations down to 0.1 picocuries per liter, 10 times more sensitive than the original equipment. They also increased the resin column size from 3 inches to 6 inches in diameter and extended collection periods from 60 days to 90. By 1966, the upgraded sand dollar stations were detecting Soviet submarines again, but at reduced ranges. What had been detectable at 50 miles now required the submarine to pass within 20 miles. The Soviets responded with additional countermeasures, improved ion exchange capacity, longer retention times before discharge, and dilution systems that mixed treated coolant with large volumes of seawater before release. Each iteration reduced the radioactive signature further. The real breakthrough came when Berkner stopped trying to detect submarines directly and started mapping the radioactive background of the oceans. Soviet submarines might reduce their signatures, but they couldn't eliminate them completely. More importantly, Soviet naval bases themselves were sources of radioactive contamination. Maintenance facilities, refueling operations, and reactor servicing created detectable plumes in surrounding waters. By establishing baseline radiation maps of areas around Murmansk, Vladivostok, and Polyarny, analysts could identify when submarines recently departed those bases based on slightly elevated isotope levels they carried with them. The approach required processing enormous amounts of data. Sand dollar stations now collected samples continuously, and shore facilities analyzed thousands of columns per year. The Navy commissioned a dedicated computing facility at Fort Meade, where IBM 7090 computers processed spectroscopy results, correlated detection patterns, and generated probability maps showing likely submarine positions based on radioactive traces. The system evolved from simple detection to sophisticated tracking and prediction. Soviet engineers continued refinement through the 1970s, but they faced fundamental physics limitations. Nuclear reactors produce radioactivity. Cooling systems require seawater. Perfect containment was theoretically possible, but practically impossible on operational submarines where reliability mattered more than absolute stealth. The signatures got smaller, but they never disappeared completely. The intelligence breakthroughs remained classified for decades, but documents declassified in the 1990s revealed how completely Sand Dollar had mapped Soviet submarine operations. Between 1958 and 1975, the network recorded over 4,000 individual submarine detections across all ocean basins. The data let analysts identify every Soviet submarine base, calculate fleet deployment rates, track technological improvements, and even estimate when specific boats underwent refueling operations based on changes in their radioactive signatures. One revelation stood out. In March 1968, Sand Dollar stations in the Pacific detected unusual radiation patterns northeast of Hawaii. The isotope concentrations were orders of magnitude higher than normal submarine signatures, and the ratios suggested a reactor that had recently been operating at very high power levels before going cold. The detection coincided with the disappearance of Soviet Gulf-class ballistic missile submarine K-129. The Navy used the radiation data to narrow the search area for the wreckage, eventually locating it in August 1968 at a depth of 16,000 feet. The subsequent recovery operation, Project Azorian, was only possible because Sand Dollar had provided the initial detection. The network also tracked the emergence of new Soviet submarine classes before visual confirmation existed. In 1971, stations near the Kola Peninsula detected reactor signatures that didn't match any known Soviet design. The isotope ratios indicated a different fuel enrichment level and higher operating temperature than previous boats. Intelligence analysts designated it as a new class, later identified as the Alpha-class attack submarine with a revolutionary liquid metal reactor. Sand Dollar detected its existence 18 months before NATO obtained photographs. The strategic value extended beyond submarine tracking. By analyzing the radioactive signatures of Soviet naval reactors, American engineers learned about Soviet reactor design, fuel cycles, and operational procedures. The data revealed that Soviet submarines typically operated their reactors at 70–80% power during patrols, suggesting either conservative operational doctrine or cooling system limitations. Their refueling cycles ran approximately 4 years, compared to 6 years for American boats, indicating lower fuel enrichment levels or higher fuel burnup rates. Declassified assessments from 1974 showed that sand dollar provided intelligence that acoustic systems couldn't match. While sonar offered tactical tracking, real-time position data for immediate threats, radiation detection provided strategic intelligence about fleet operations, deployment patterns, and technological capabilities. The combination of both systems gave the Navy comprehensive coverage. Sonar for hunting submarines in specific areas, sand dollar for understanding where those submarines came from, where they were going, and what they were doing. The network's operational impact appeared in contingency planning documents. Navy war plans from the 1970s relied on sand dollar data to predict Soviet submarine deployments during crisis escalation. The models showed that when tensions increased, Soviet ballistic missile submarines typically deployed to patrol areas in the Barents Sea and Sea of Okhotsk within 72 hours. Attack submarines moved to forward positions near NATO naval bases within 96 hours. This knowledge let NATO position anti-submarine forces preemptively rather than reactively. By 1976, the network included 93 permanent stations, 12 rapid deployment vessels, and 5 shore processing facilities analyzing approximately 8,000 resin columns annually. The program budget had grown to $18 million per year, still less than a single P-3 Orion patrol aircraft, and the intelligence value was considered irreplaceable. Even as satellite reconnaissance improved and acoustic arrays became more sophisticated, sand dollar remained the only system that could track submarines across entire ocean basins and provide continuous monitoring of Soviet naval reactor operations. Berkner retired from the Naval Research Laboratory in 1977, but the program he created continued operating under successive technology upgrades and expanding mission requirements. The sand dollar network officially declassified in 1991 after the Soviet Union collapsed, but the sensors didn't stop operating. The technology Berkner developed for tracking submarines proved equally valuable for monitoring nuclear weapons testing, detecting clandestine reactor operations, and enforcing non-proliferation treaties. The same physics that revealed Soviet submarine movements could identify any nation operating nuclear reactors near coastal waters. The Comprehensive Nuclear Test Ban Treaty, signed in 1996, relied partly on radiation detection networks descended from Berkner's original designs. When nations conducted underground nuclear tests, radioactive isotopes sometimes escaped into groundwater and eventually reached the ocean. The detection stations could identify specific isotope signatures that indicated weapons testing versus civilian reactor operations. In 2006, sensors off the Korean peninsula detected trace amounts of xenon-133 consistent with North Korea's first nuclear test, providing independent verification beyond seismic monitoring. Modern versions of the technology monitor the world's oceans continuously. The sensors evolved from hand-built prototypes to automated systems that transmit data via satellite, use solid-state detectors instead of scintillation crystals, and employ machine learning algorithms to distinguish between natural background radiation, legitimate reactor operations, and suspicious activity. What required 6 hours of laboratory analysis in 1960 now happens in near real time, with detection thresholds 100 times more sensitive than Berkner achieved. The Navy still operates radiation detection networks, though current capabilities remain classified. Publicly available information suggests coverage extends to monitoring Russian and Chinese submarine operations, tracking civilian nuclear vessels, and providing early warning of radiological incidents. When the Japanese Fukushima reactor failed in 2011, American detection stations track the dispersal of radioactive isotopes across the Pacific, providing data that help predict contamination patterns and assess environmental impact. The fundamental concept remains unchanged. Nuclear reactors produce unique radioactive signatures, and those signatures persist in seawater long after the source has moved on. Physics doesn't care about stealth technology, acoustic dampening, or electronic countermeasures. A submarine running a nuclear reactor will leave traces in the water, and sufficiently sensitive equipment will detect them. Modern submarines have better containment than Soviet boats from the 1960s, but perfect containment remains elusive. Berkner's legacy extends beyond the specific technology. He demonstrated that unconventional approaches could solve problems traditional methods couldn't touch. When everyone focused on making sonar more sensitive, he asked whether sound was the right thing to detect in the first place. When experts said the concentrations were too low to measure, he found ways to concentrate them. When the Navy wanted immediate tactical data, he convinced them that strategic intelligence over weeks and months was actually more valuable. The engineer who started in a basement laboratory with borrowed equipment and a $12,000 budget created a surveillance network that operated for over 30 years and fundamentally changed how nations monitor submarine operations. His sensors tracked Soviet submarines through the Cuban Missile Crisis, mapped Soviet naval deployments throughout the Cold War, and provided intelligence that shaped American naval strategy for decades. The technology he developed still monitors the world's oceans today, detecting threats that acoustic systems miss and providing verification for international treaties. Berkner died in 1967, only 9 years after deploying the first operational sensors. He never saw the declassified intelligence reports showing how completely his system had mapped Soviet submarine operations, never knew about Project Azorian, and never learned that the admirals who walked out of his first presentation eventually admitted he'd been right. But the network he built continued operating long after his death, proving that sometimes the craziest ideas are the ones that work.